So in this video, we are going to review for the quiz over 1.1 and 1.3. So looking at those notes, looking back at those homework, or any of the videos I've created on those sections would be helpful. The first thing I'm going to ask you is, are these functions of x? So if you know what the graph looks like, you're going to use the vertical line test. Remember, a vertical line can only hit a function at most one time. So this one here is not a function. And this one is a function. Now, if it is y equals, if it can be rewritten very easily as function notation, that's a good indication that's a function. This is a yes. But if you know that that is a parabola, and parabolas pass the vertical line test, then you can also say yes. Now, the next one here, if you have a power on your y, or if your x and y, if you have like mixed up x's and y's, that's a really good indication something's wrong and it's not a function. This is a circle with a radius of 2. You might recall x squared plus y squared equals r squared. It's like the most simple type of circle function. A circle doesn't pass a vertical line test. It's a no. So if you have an absolute value on a y, an even power on a y, it's not going to be a function. Now, ones that are just a discrete set here where we're listing the points, just look at the x's. If the x's repeat, it's not a function because those would line up vertically. But if the x's are all unique, like in f, it would be a function. So that's just a little bit about what makes something a function of x. Next, we need to know how to use a function. So we have this function f of x equals 17 minus the quantity of x squared. So make sure that you put your input, in this case 3, into parentheses. Following order of operations, we've got to square it first. So 3 squared is 9. That negative is not in the square, so we're just going to leave it there. And then you do 17 minus 9, which is 8. Now, if you give me the ordered pair for any numerical stuff, I'll throw in a little bonus point for you. So I inputted 3, I got out 8. Let's do it again. This time my input is -2. This is really an important one to put that in parentheses. So we remember, we got to do -2 times -2. We got to square that -2 first. It's going to become a positive, but when we take the opposite or subtract a positive, if I would actually square, then that negative out in front just stays along for the ride. You can almost think about it as a negative times a negative times a negative. You've got 3 negatives there in this little arrangement here. So that's why it's going to stay negative. And then 17 minus 4 is 13. I input -2. I get out 13. Now in C here, you'll notice when we're going to input something, it has an x in it. Well, you're just still taking out the x and replacing it with 2x. To do that, you're going to do 17 minus that input squared. So just put your 2x right here. So when you do that, you have to square the 2x first. So it would be 17 minus 4x squared. Now the hardest one on this list is the bottom one. Not the input necessarily. That's just 17 minus that thing squared. So we're inputting our x plus 1. It's just the simplification that I've noticed. So don't forget that x plus 1 squared, it's a good idea to write 2 of them so that you remember that you got a FOIL. Now, if you do that multiplication, you get x squared plus x plus x plus 1. Now, let's go over that. The x is used twice. That's the first 2. The 1 is distributed and used twice. That's the last 2. And then if we simplify that, we get x squared plus 2x plus 1, okay? So just make sure that you're multiplying that correctly. Now, we are subtracting that x squared plus 2x plus 1. So leave it in parentheses until you have distributed the negative to all of the pieces. So it would be 17 minus x squared minus 2x minus 1. Now you only have one more step to go. 17 minus 1 is 16. You can write the 16 in the front. I like to go in least to greatest order, so I've got a negative x squared, a negative 2x, and a positive 16. I like to write it like that because eventually that is going to be helpful to us. It's just a good habit to get into. So there is inputting into a function. X and y intercepts from a graph. To find the x-intercepts of the graph, we are looking for where does the graph touch the x-axis. And we can clearly see that our x-intercepts are, in this graph, negative 3, 0, and positive 3, 0. I like you write them as a point. You can say, if you give me a little information, that the zeros are negative 3 and positive 3. If you give me that extra piece of information, I will give you a bonus point there. And then this graph B, you'll notice we have 3 of those. And so the x-intercepts there are the points negative 3, 0, 1, 0, and 2, 0. And you can say then the zeros are, let's put equals like the last one, negative 3, 1, and 2. Now, zeros or x-intercepts are where we hit the x-axis. Y-intercepts are where we hit the y-axis. Now, if it's a function, there should only be one of those, and these are functions. So the y-intercept is the point 0, negative 9. Now, it doesn't really have its own little special term for it. It's just the y-intercept. And then in this one, that would be this point right here, which is 0, 6. So that's how you find the intercepts from the graph. Now let's talk about the domain and range of the graphs above. The domain of both of these, as this graph goes, it's going to stretch from left to right as far as we want. So the domain of A is all real numbers. And you can write the word all real or just make that R with that fancy bag. The domain of this is all real numbers. Those are examples of a graph of polynomials. The domains are all going to be nice and pretty and great, you know, so they're all real numbers. Now the range is what y values came out. What heights does this graph go to? This graph has a lowest point at that y-intercept of negative 9. So it can be anything from negative 9 up. Now I want that in interval notation when it's an interval. I mean, here we could do negative infinity to positive infinity. That's all reals as well. But you can just tell me that it goes from negative 9. It's included. It's a point on the graph. And it can go up as high as you want. I mean, technically, it's the y's are greater than or equal to 9. Or negative 9, I'm sorry. Here, our range. Now, what's interesting about this one is this goes down as far as we want to. We can go then up as high as we want to, and we don't skip any heights in between. So that is all real numbers, or again, you could write interval notation with negative infinity to positive infinity means the same thing. Now, the last question here is asking about the end behavior. Now, remember the notation, the left end and the right end. Left end and right end. Okay, now let's talk about the notation. And if you say that the left side of this graph goes to positive infinity and the right side of that graph goes to positive infinity, up, that's correct. I'm going to give it to you. If you tell me this left side's going down to negative infinity and the right side's going up to positive infinity, that's correct. I'm going to give it to you. But if you use the correct calculus notation, I'm going to give you a bonus. Now, what do I want? So you would say here, and we're just going to call these f. You can call them f, g, h. Those are common for functions. If you go the limit as x goes to negative infinity of my function is positive infinity, And the limit as x goes to positive infinity of my function is also positive infinity. That's going to be bonus. So if you use the correct notation, I'm giving it to you, okay? Same thing here. Limit as x goes to negative infinity is negative infinity, down. Limit as x goes to positive infinity, the function is going up, positive infinity. So this is referring to left, right, and this is referring to up or down, up, or these ones were up, this one's going down. Okay, so you make sure you understand for our graphs the intercepts, domain and range, and end behavior. Okay, now let's talk about using a piecewise function. So we've got a piecewise function here. Let's analyze it first before you jump in. If we're plugging in any values between, less than or equal to 0, the answer is just 0. You don't really have to do any math. They've kind of done it for you. Any numbers between 0 and 10, including 10, is take that value, divide by 2. And then any number that is bigger than 10, we're going to plug it in here, and we're going to add 1. Okay. So our first value here of -1. -1 is in this category, so the answer is 0. I don't have to do any math. It's just 0. Okay. 8 is between 0 and 10, and so that would be 8 over 2. You would use this function here, and 8 over 2 is 4. Let's go with 10. Now 10 is a border value, so wherever the equal to bar is the one you're going to use. So if we would use that middle one again, so that would be 10 divided by 2, or 5. 12. 12 is bigger than 10, so we would use this one. It's just 12 plus 1, or 13. Now it says the following questions. Is the function continuous at 0? Is the function continuous at 10? Now, piecewise functions are going to be discontinuous most of the time if on the border there is a jump between the functions. So how do we check that? So let's go back up here, and let's check our first border of 0. If I plug 0 into this function, I'm at a height of 0. And what we want to know is, does this border match up? So the top one gives me 0. The bottom one would be 0 divided by 2, which is also 0. They match, so that's yes, it's continuous. Okay, now let's go back up, and now let's discuss the other border, 10. Okay, now we're going to plug 10 into both pieces. If we plug 10 into here, 10 divided by 2 is 5. If we plug 10 into here, 10 plus 1 is 11. 5 and 11 don't match. They are different. So there's a jump there in the graph at that point, so that's a no. So for continuity in a piecewise function, you're just checking the borders, and you're saying, hey, do the border values match if I plugged the border value into the two border pieces? And that's how you find that. Okay. So that's a piecewise function. Let's talk about domain of a function. The domain of a function, if it is a polynomial, I can plug in whatever the heck I want. So because of that, the domain is all real numbers. So let's write that in interval notation, okay? So I can plug in whatever I want. I can plug in positives, negatives, fractions, decimals, anything I want into x squared plus 2. That graph stretches from the left and the right. It's a parabola that's opening wider and wider and wider. So yeah, we're good, okay? For a square root, here's the rule that you have to remember. You got to take the inside and set it greater than or equal to 0. So just set that inside greater than or equal to 0. It's just an inequality, and solve. And if you divide by negative, remember to flip the symbol. Otherwise, it is what it is. We're going to add 1 to both sides. We get x is greater than or equal to 1. On the number line, that would be from 1 getting bigger to infinity. So that's a square root. Inside greater than or equal to 0 is the rule you want to memorize for a fraction. This is a rational function. If it's a rational function, the denominator is not allowed to equal 0. So just take that denominator, set it equal to 0 with a slash through it, solve it to find the x value you're not allowed to equal. If I add 1 to both sides, I get x is not allowed to equal 1. So the domain here, we can use anything before we get to 1. We can use anything after 1. You'll notice there's a little gap because those are parentheses only at 1. Everything to the left of 1's fine. Everything to the right of 1's fine. This kind of tells me I skipped 1. Okay? Okay. So then let's take a look at 8. It says describe the discontinuities for the function. So here I'm looking at -3. I'm looking at 0. I'm looking at x value of 2. I'm looking at an x value of 5. I'm looking at an x value of 6. Okay? Now, just take a minute, pause the video, and try to draw this graph on your paper. There's graph paper over on the counter. Feel free to grab some graph paper. So first, let's take a look at this point here. If x is equal to -3, see how we're getting ever so close there, but there's a hole. So if you put a hole, that's fine. That is considered mathematically, the terminology for that is a removable discontinuity. And feel free to just write the word removable, okay? Let's take a look at this one. See how the two pieces have not come together? That is a jump. So if the pieces on one side are at 1 height, 0, this side's at 3, the heights didn't match. They did not come together. If they came together, it'd be a different reason, but they don't come together. So that's a jump. At an x value of 2, there's still a hole there. The spot's in the wrong spot. They didn't remove the issue. They just moved it somewhere. It's still removable. Here we have a colored in dot. The left side comes to it. The right side comes to it. It's okay the way it is. There's no discontinuity there. And this one, see how it's got an asymptote that it's following, getting closer and closer. That is called an infinite discontinuity. That's a vertical asymptote. It is an infinite. So I'm going to give you a weird graph like this. I'm going to list the points I want you to look at. If there's a hole, write down removable. If there's a disconnect and you had to jump to the next piece, that's a jump. Again, a hole is removable. If it just continues and you didn't have to lift your pencil, it's okay. And then here, you're following a vertical asymptote. It's called infinite. So you got to study those, okay? Last things on the review. Let's look at 9. It says, describe the discontinuities at these points. So really, we're looking at two different things, okay, for the fractional ones. So let's focus first on A and B. Okay, for the fractional ones, what you're looking at is if you plug into the function and you get a number over 0, you have found an infinite discontinuity. You found a vertical asymptote. Okay, but if you get 0 over 0, you actually have found a hole. You have found a removable discontinuity. Okay, so let's do A and B, and I'll show you what I mean. Okay, if I plug -2 into the function, I get 1 over 0. I just found a vertical asymptote. Now, if you don't believe me, go and plug the function f of x equals 1 over x plus 2 into Desmos. Zoom in at the point x equals -2. You're going to hit a vertical asymptote. Let's take a look at B. For B, if I plug -2 into this function, I get 0 over 0. I have just found a hole in the graph. Now, if you type that graph into Desmos and you go to the spot where x is -2, you won't see that hole like we physically put it on the graph. Decimus can't really do that. But if you take your mouse and you scroll past that point, it will say -2, comma, undefined. So and the hole will show up there. I don't know why they don't just physically put it on there. It's just, to me, a little glitch in the system. But yeah, it is a little hole in the graph. We can't really see it on Decimus, but we would draw it and put a little hole there. Okay, last one. We had done this one already. The border is 10. If I plug 10 in here, I get 5. If I plug 10 in here, I get 11. They don't match, so there is a jump. So if it's a piecewise function border, most likely if there's a problem, it's a jump. If I picked a value of 7, it's within a nice continuous spot. So it's continuous at that point, even though at another point there's a problem. So continuity is kind of almost point by point or section by section. So if that makes sense at all. Finally, the last function, or the last thing you need to know for the quiz, is how to determine if a function is even or odd. If you stick in -x, and it goes right back to where it started, so it matches the original, it's even. Okay? I'm sorry, I went parenthesis crazy there a little bit. It looks so weird. I'm going to fix it. Okay. Anyway, that's original. If you stick in -x and you get the opposite of the original, it's odd. Okay. It has origin symmetry. I'll give you a bonus if you tell me the symmetry. This one would be y-axis, and this one is origin. Okay. Let's take a look at our first one. If I stick in -x, I get the opposite of x squared plus 2. If I square negative, it's going to become a positive. So that's x plus 2, or x squared plus 2, which is exactly the original. So that is an even function. It has y-axis symmetry. So again, all you have to say is even or odd. If you tell me y-axis, guess what? You're going to get a bonus. Let's take a look at B. If I stick in -x, I get 2 times -x, which is -2x. That is the opposite of the original. So it's odd. It has origin symmetry. Okay, let's do it one more time. If you stick in -x, you get -x cubed minus 3 times -x plus 5. So we're just taking out the x's, sticking in -x in parentheses. We're going to simplify down, see what the heck happens. We get -x cubed plus 3x plus 5. Now, it doesn't match the original. Just compare it. I always go first in my brain. Hey, does it match the original? Nope. So it's not even. Then I say, are all the pieces the opposite of the original? Opposite, opposite. Ooh, that piece isn't. So it's not anything special. It's neither. It's not even. It's not odd. And you can check those as you're doing your math. If you throw them into Decimus, now you can't use that on the test, but if you throw those into Decimus, the top A is foldable over the y-axis, has y-axis symmetry. B is origin symmetry. C is neither, okay? So this is what's going to be on the quiz. It follows this order, follows this kind of model. So this is what you want to study. This is what we're doing in class Tuesday, but posting it early if you're going to help me with the blood drive or anything else, you can study it. And to do math is to study math. So thanks, guys.